Okay, so thanks very much. First of all, I should say, if the volume goes down, please just yell at me and I'll bring it right back up again, okay? Thanks first of all to the organizers for this really fantastic, stimulating meeting. I really learned a lot of things here. Thanks also for the invitation to give this talk. So what I'm going to do in the next 25 minutes is tell you about spin symmetries. We already heard about spin symmetries in the context of altermagnetism and also in the more broad context of electronic band structures from SPICE-JGU on Tuesday. And what I'm going to do today is give a slightly different perspective that concentrates more on local moment systems. So we're really going to deal with isolated spins in the spirit of the previous talk. Okay, so first of all, before I get into the physics, let me just highlight PhD student Alberto Caccicelli at MPI PKS, where I'm based, and Roderich Mörsner. So this is one work from 2022 that I'll tell you about. And then I've also been collaborating with Alex Muck at Mainz, Matthias Golker at Okinawa Institute for Science and Technology, and some experimentalists, Alan Shea and Steve Nagler, and a theorist, Pontus Laurel at Oak Ridge National Lab. Okay, so just to introduce things in a relatively gentle way, for this audience, I absolutely don't need to impress on you the importance of symmetries. They're essentially the foundation for all of crystalline solid-state physics. What we do is we ask questions like, what are the transformations that leave crystal structures invariant? This consists of a set of discrete translations, rotations, mirrors, and combinations. This line of thinking dates back a very long time, a couple of hundred years, when the point groups for crystalline systems were first enumerated, resulting in 230 space groups for full crystals towards the end of the 19th century. And when quantum mechanics came along, this became central to constraining, for example, features of band structures, response functions. There are extinctions. When things are allowed by symmetry, often they appear in actual measurable quantities, as we've been discussing during this meeting. So after these crystalline symmetries, there came the next step of thinking about magnetic structures. So now the natural context here is you put a local moment on the sides of the lattice, so something like this or like this. And you can classify them by introducing the idea of time reversal symmetry, where you flip local moments under the time reversal operation. And you also constrain, you also have these point group symmetries like rotations and reflections and so on that lock the spatial and spin transformations together. Okay, so this is the underlying assumption that goes into classifying the so-called magnetic space groups, which now expand the number from 230, the lattice groups, to 1651. Now, as I say, a central underlying assumption here is that the spin-orbit coupling is sufficiently strong that when I say rotate the crystal, I rotate the moments along with it. But this is an assumption that you can relax. And it's naturally relaxed in the cases of, I will call it, in inverted commas, weak spin-orbit coupling, and I'm going to clarify what I mean by weak spin-orbit coupling as I go through the talk. So the general idea is that rather than having operations that act on spin space and on real space at the same time, instead I'm going to split these into two. I'm going to have operations that act on real space and on spin space in principle separately. So for example, here I have an identity element acting on spin space and a C3 acting on real space. So I'm rotating this triangle, but I'm not doing nothing to the moments. I'm taking one moment to another site, but I'm not changing its orientation. Now, the recognition that these groups could be important came maybe around a decade or two after magnetic space groups became a thing. in particular with the work of Kitz and with Brinkman and Elliott working in Oxford. And then these ideas were systematized in the early 1970s by Litvin and Opachovsky. And what they noted was that these groups take this rather general form, where this is a group that has elements like this, where spin and space transform together, but notably, there are no elements where the spin transforms alone. The elements where the spin transforms alone are included in this B, so this consists of a set of spin-only elements, and this is going to be important for various applications later on in the talk. So let me just pick up on this. So this group GSS, which contains spin and space elements, is generally anti-unitary. So in other words, it contains spin and space transformations as well as time reversal elements. And just to give you an impression of the numbers here, we went from 32, let me just concentrate on point groups. If I just think about crystallographic point groups, there are just 32 of them. When you go to the magnetic point groups, again, locking spin and space together, you get to 122. And as Litvin recognized in the 1970s, there are 598 of these spin point groups. Now, as we heard from Chihang on Tuesday, this B group is actually it's actually constrained by which of these GSS groups that you choose, but I won't go into that in too much more detail. Let me instead try to give you a more physical perspective on all of this, and most of this talk is going to be concentrating on physics. So as I said, when you're in the strong spin-orbit coupling limit, you expect to lock spin and space transformations together, and when you switch it off entirely, you expect spin space to be completely indifferent to what's happening in real space. So what that means, when there's no spin-orbit coupling and we take a local moment picture, so we're thinking about moments on individual sites, we expect there to be full spin rotation symmetry. So this has full spin rotation symmetry, and if we go back to the previous talk, we can have also powers of this in principle, and this acting on more and more sites. Now, I can add a certain type of spin-orbit coupling that gives an easy plane or an easy axis anisotropy to the moments. And what that will tend to do is, for example, break this down from full rotation invariance to just a U1. Okay, so just a rotation invariance in the plane. You still here have a continuous spin rotation symmetry. Now, what I can do further, in the previous talk we heard about systematics of Dirijinsky-Maria. Here's one such Dirijinsky-Maria with a D vector pointing in the Z direction. And what we have here is actually a U1 symmetry left over. So this doesn't break you down to a discrete set of symmetries on its own. But if I have a general Dirijinsky-Maria, depending on the symmetry of the crystal, this can actually be broken down to some discrete set of symmetries. And in the completely general strong spin-orbit coupled case, you can end up with, in this case, bilinear interactions between moments on different sites that are highly anisotropic in nature and generally break down the symmetries to those of the crystal. Here, the constraint is that we're really locking the spin and the space systems together.
Why you don't allow JZZ, like Eisenberg interaction in your second line?
Oh yes, I could also have JZZ, absolutely. Yeah, so this isn't supposed to be exhaustive. So now let me go to a particular example. I'm going to talk a lot about magnetic excitations because this is a natural context to think about these spin symmetries in rather great generality. So I'm going to focus on MNF2, rutile, that we've come across a lot over the course of this conference. This has a collinear antiferromagnetic structure along the C direction. This is tetragonal with this body-centered form, but notably you have these fluoride ions that break down some symmetries. Now, in manganese, the spin orbit, the orbital moment is completely quenched. So you have a pure spin moment of 5/2. It's a large moment. And on the basis of this zero orbital moment, we just expect there to be pure rotational symmetry. So this is a natural Hamiltonian to write down between, say, sites A and B. And that perfectly accounts for the observed magnetic structure up to the fact that you get this C-axis ordering. Now, if you just had this Hamiltonian, you'd expect there to be a doubly degenerate Magnon spectrum. And the reason for this double degeneracy is strongly related to residual spin symmetry. So in particular, there's a spin, when you magnetically order, you break the continuous rotation symmetry down to a U1, or SO2. And what this means is that this preserves the integrity of the bosonic operators on sites A and B, but with a dagger between them. These transform in exactly the same way under rotations. And a more technical way of saying this is that the irreps, the irreducible representations of U1, take this form with integer n, and this integer n1 is just, plus or minus 1 is just preserved by these combinations, and by also the combination b of k, a minus k dagger. Okay? So what this means is that you have a well-defined chirality, essentially the phase angle of each of the Magnon modes. And moreover, if I didn't need to worry about these fluoride ions, I could just transform, there would be a mapping, like an inversion mapping between these two, that would, PT symmetry, I should say, that would make these sublattices equivalent. This would make the two well-defined chiralities degenerate. Okay, so that's the overall reason why you get this full degeneracy. Now, with full rotational symmetry, if I didn't only think about this spin part, so this B group that I pulled out in previous slide, and I thought about the GSS group, I would get something like this in the presence of these fluoride ions. So the critical point here is that actually I do break down the equivalence between these two sublattices under inversion, but these can be rotated into one another under this C4 with a translation, so from one to another. But in spin space, I should be doing something different. So I should be rotating just by pi. So this has this non-trivial GSS spin symmetry, and it also has this zero spin orbit coupling SO2. And both of these together are important for the Magnon spectrum. So the effect of this only C4 in here, this C4 times this spin C2, is that I get inequivalent couplings JD across this plane and this coupling here. So these are not related by symmetry. This has the effect of breaking this degeneracy, but rather unusually for Magnons, it preserves the U1. So usually you would break the U1 before you break anything else. The funny thing about this is that you're breaking down the crystalline symmetries before you break down the U1, so you get well-defined chiralities, but at the same time, you're breaking the degeneracy between these modes, almost everywhere in the zone. So clearly at the zone boundary, the degeneracy is preserved, and also at the gamma point. Okay, so let's take a look at some experimental data. It turns out that there's a spin gap. The spin gap tells us that this minimal model is not correct. This is perfectly consistent with the fact that you have a c-axis moment. The c-axis moment together with this spin gap tells you that you have some anisotropy in the system, and sure enough, because this is a large moment system, there is a significant dipole interaction. This is the estimate for the nearest neighbor dipole. This is much smaller than the size of the spin gap, but there are 8 nearest neighbors. So this is probably consistent with the presence of a dipole, but say between these neighbors here, that gives you an effective easing type coupling. So that preserves the chirality, it preserves the U1, it preserves the other symmetries. What you can see also is that if you go along this direction or along this direction, there is a different dispersion. Okay, so there's a further kind of splitting. This is not the altermagnetic splitting, I should say. The altermagnetic splitting has not been observed so far. Maybe the splitting is extremely small. But I would say there is some hope for seeing this in this kind of system. For example, if you compute the intensities, it appears that they have equal intensities along the 110 direction. So in principle, they should be both seen without having to do multiple scans. And secondly, it should be possible to do some more sophisticated neutron experiment, like a neutron spin resonance experiment, which has much higher energy resolution in its typical setup. Okay, so this is one example of how spin groups are important in, potentially important in real systems. So both for the Heisenberg case and for the both for the Heisenberg case with nearest neighbor couplings between the different sublattices, and also in the altermagnetic case. Here's another example. This is something that I'm also going to think of as a local moment system, but it's a metal. It's gadolinium metal. Once again, even though this is a rare earth, the orbital angular momentum is quenched, so you only get it from mixing. It's metallic. It's well described by RKKY with a spherical Fermi surface. There is extensive neutron scattering data that fits exchange couplings to further neighbor. You get this oscillating ferromagnetic, antiferromagnetic sign as a function of distance, consistent with RKKY. And notably, what I want to tell you is that there are well-defined nodal lines running along the zone corners, and also there's a nodal plane sitting top and bottom of the Brillouin zone. Now, this is something that you wouldn't expect in a strong spin-orbit coupled system. The way that this can happen at all is because there is a residual spin space symmetry. In particular, there's a preserved time reversal symmetry. And the time reversal symmetry is essentially coming from a C2 perpendicular to the moment times time reversal. This is an effective time reversal symmetry that gives you preserved masslessness at these points. These are these Dirac points here. And then on the top, this can be shown to be due to an effective time reversal. Again, this is a C2 spin perpendicular times time reversal times this real space part, which is a non-symorphic symmetry, a C2 times a translation in the C direction. So this is yet another example of how spin groups are important to specifying the band structures in Magnons, and also specifying topological features, so Dirac nodal lines in these kinds of systems. Now let me just try to give you a slightly broader perspective. So I just argued that you get an effective time reversal in this gadolinium system coming from a C2 perpendicular spin times time reversal. But you can get also time reversal preserved in magnets in a more conventional way by having two sublattices that are related, say, by an inversion symmetry, but then you flip also the moments. So say from this D to the B, you get a flipping of the sign and a change of the moments under inversion. And this also can preserve Dirac nodal lines. This has been demonstrated in this work here. Okay. So far I've been telling you about spin symmetries with continuous rotation symmetry. But this is not the end of the story. There are actually spin space symmetries that are present even when spin-orbit coupling is in principle strong. And they instead are discrete spin space symmetries rather than continuous. So I'm going to give you an example. I'll try to be brief. How much time is there remaining?
A lot. 5 to 10 minutes.
Okay, excellent. Okay, so I'm going to tell you about a certain class of Kitaev systems. In particular, first of all, Kitaev systems on a hyper-honeycomb lattice. This is an orthorhombic system with 4 magnetic sublattices. So expect 4 Magnon bands if you don't break down the translation symmetry. And a natural way of describing certain spin-orbit coupled hyper-honeycomb magnets is through this Heisenberg term plus a Kitaev term. Now, the meaning of this Kitaev term, this is extensively discussed these days, but I just say that the interaction here is between nearest neighbors, and it's an Ising type interaction, so that's why these gammas are the same for the different spins. And the gammas cycle over XYZ, and these XYZ are matched to the colors that you see here, so green, red, and blue. Okay? Now, this has perfect spin rotation symmetry in the paramagnetic phase, but this breaks it down. But it doesn't break it down to the crystal symmetries. It breaks it down to a D2. So what you can do is a C2 rotation parallel to X, Y, and Z axes, and this preserves the paramagnetic state, or preserves the Hamiltonian. So there is a discrete spin space group lurking within this model, and what I'm going to tell you about is some of the implications of this. So let me take, first of all, an example. What I'm going to do is take the Néel phase of this model. So I'm taking this to be broadly antiferromagnetic, and then persists on either side of the Heisenberg antiferromagnetic point when you switch on Kitaev. This is just a generic point in the phase diagram, and what you see is an extremely rich band structure in the Magnons. There are 4 Magnon bands, and these 4 Magnon bands have a nodal plane here. They have a loop, they have multiple nodal lines elsewhere, and notably a fourfold degenerate point, so a high degeneracy point that you can see here. Now in the Heisenberg limit, you just go to a full volume degeneracy. As I told you before, it's exactly the same reasoning that we had for the manganese difluoride case. And in the Kitaev limit, it's even more exotic. So one can understand all of these features on the basis of spin space group theory. So essentially what you do is you break down the paramagnetic symmetries, which have this spin group D2, down to the magnetic order. And when you do that, you start to couple the spin space and the real space transformations to one another. So you get a non-trivial, if you like, GSS group that I told you about earlier. So I'm not going to dwell on this long table. You don't need to get much from this, except that you can characterize all of the unitary and non-unitary symmetries that are present for lots of different kinds of phases, including the Néel phase that I just showed you here. So here are some different phases that we investigated. So there is a ferromagnetic phase, so all moments in the same direction, but notably for different moment orientations. So the band structure changes qualitatively when you change the moment orientation because of the Kitaev term. And then we look at these different phases as well. And as you can see, the group is generally changing as you go from not only one phase for another, but also for different field orientations. One of the main points that I want to impress on you is that you can carry out, you can look for isomorphisms between the spin space groups and actual magnetic space groups. Here is a list of ordinary magnetic space groups, and it turns out that these spin space groups can be isomorphic to these magnetic space groups, occasionally multiplied by a pure spin part. Okay, so this, I think, is an important observation. Essentially, what you can do is do something that a crystallographer would do. You look at the magnetic structure, and then you characterize, assuming that the spin and space are locked together, what the magnetic space group is. And then you can ask yourself, in contrast, what happens if I just look at the Hamiltonian, break down the symmetries for some magnetic order, and then ask what the symmetries are? Now, naively, you'd expect those two to match, but in general, they don't match. Instead, you hop to a different magnetic space group that you wouldn't have naively expected in the first place. And this has important consequences for topology. So let me show you. So here's a table showing the expectations for degeneracy for the underlying magnetic space group that you would expect purely on a structural refinement, and also from the spin space group that you get from the full Hamiltonian with the broken magnetic symmetry. So what you see is that the degeneracy present in the spin space group is massively enhanced, usually, over that of the magnetic space group. And so the topology is greatly enriched. Moreover, so this is a pictorial way of looking at this kind of at this scenario. So what you can start with is the full Heisenberg paramagnetic group, which is the full crystalline group plus time reversal times the same group, multiplied by the full spin rotation symmetry. So that's the most symmetric case. The least symmetric case is just for a random orientation of a ferromagnetic moment in spin space. And then what you can do is you can hop from one group to another, often just by reorienting the moment. And what I'm doing here is distinguishing between cases where you move the moment into some direction, and you get to a new group here, which is labeled by a magnetic space group label times a spin part. And this is an ordinary magnetic space group, the dark color here, an ordinary magnetic space group that arises both by enhancement from this just by a field orientation. So this space group can arise from this particular magnetic space group can arise from a magnetic structure that you would not have expected would lead to this particular magnetic space group. On the other hand, you can start from something where the crystal structure or the magnetic structure does tell you that you have this symmetry, and then you can enhance it further to something like this. So the main message here is that when you go to these spin space groups, you massively increase the number of symmetries that you can have, and naive crystallography based on magnetic structures ceases to be the way to go. What you have to do is know precisely what the Hamiltonian is in order to infer what the physics is. So this is true in this system, and it's true in many other systems. This is just for this orthorhombic space group 70 case, but one can in principle do this for every other kind of system. And then finally, what I want to do is go to a much simpler case, also Heisenberg, Kitaev, but just a honeycomb. So now the honeycomb Kitaev is much easier to visualize. You get these red, green, blue bonds corresponding to the X, Y, Z Kitaev axes. This is a system of great current interest, in particular because alpha ruthenium trichloride is a honeycomb antiferromagnet with strong spin-orbit coupling that seems to have a very strong Kitaev coupling. In this system, there's a thermal Hall effect in this magnetic insulator. This thermal Hall effect arises when the moments are polarized along the field. So it's natural to study this Heisenberg-Kitaev model in this context, and in fact, a concrete mechanism for the way that this can arise is through the Berry curvature in the Magnon dispersion relations. So what one can show is that across this entire parameter space, except for the Heisenberg points, you get degeneracy breaking of the two Magnon modes. They have non-zero Chern number. They have, therefore, non-zero Berry curvature, so there's a thermal Hall effect for certain field orientations. So what one can do is just rotate the moments, and then it turns out that along these meridians, so just these meridians here that are sketched in black, the touching point between the two Magnon bands actually closes. You get a Dirac point. So you get an emergent time reversal symmetry, and the way that this happens is that you get this emergent spin space symmetry, so this C2 spin times a time reversal that protects Dirac Magnon points along those meridians, and everywhere else you get Chern Magnon bands. Okay, so I've reached the end of the talk. I'm just going to put up this summary. I would just say in a broad context, we're just as with altermagnets, we're just beginning to explore this territory. There's a massive space of symmetries to explore here, especially their consequences for physics. We saw this on Tuesday. We saw it today. We've been seeing it with these altermagnetic systems, and I'm excited to see what comes out of this. So thank you very much.
Thank you.